Hey guys, and welcome to our first lesson in Unit 7. This unit will be discussing simple harmonic motion and oscillating systems. So we're going to start by introducing the concept of oscillating systems today. So our first 6 units, we talked about ways to describe motion and energy and momentum that could be applied pretty broadly to almost any system. However, in these last 2 units of our course, we're going to take a look at some specific types of systems and objects. And next unit, we'll take a look at fluids. And this unit, we'll take a look at systems that are moving in a very specific manner, a manner that we call oscillation. So what we'll do here in the beginning is we're going to take a look at 3 different systems that are undergoing oscillating motion. And as we take a look at them, I want you to be considering what quantities it would be really easy to measure in these systems. So by easy to measure, what I mean is things that we can measure using a meter stick or a scale or a timer, things we can directly measure about these systems. And then after you think about that, consider what quantities would be a little bit harder to measure, but that we could do if we use those original quantities we measured and use them to calculate some new values, or if we have some more advanced equipment, what sort of things can we measure then about these systems? All right, so let's take a look. All right, so what we've got here is a bootleg little oscillating system I've set up. We have 2 of our motion cards. They're attached together, and then on each end, they're attached by a spring to these barriers. All right, so the center mass of our system sits at about 60 centimeters here on our ramp, and the spring on each side have roughly the same spring constant on the left side as they have on the right side. So what we're going to do is we're going to displace the center of mass of this system in one direction. We're going to see what happens, all right? So if I pull these guys over to, let's say, 55 or 53 centimeters over here, and then release them, they now been pulled away from that center where they like to sit, and now they start going through, and this is what we call oscillating motion. All right, so we're going back and forth, and they're repeating that motion over time. So that one's super strong, and then they eventually die down. So let's pull them a little bit further on one side. We'll see our oscillating motion gets even larger when we pull further away. So what I want you to think about is what are some things we can measure here with a meter stick and a timer, and that we can measure directly, and then what are some things we can measure on top of that using those values we can either calculate for, or if we had more advanced equipment, what else can we measure here? All right, so for the next system we're going to take a look at, I've got a nut on a string attached to our ring stand over here, all right, and this creates a little pendulum bob. So this is where the pendulum wants to hang out. This is what we would call our point of equilibrium. But if I displace the pendulum bob away from that, we end up with, again, oscillating motion, going back and forth and repeating ad infinitum until eventually friction or some non-conservative force slows the system down back to 0. And for our final oscillating system that we use to introduce this whole concept of oscillation, I've got a weight on the end of a spring. And so obviously this spring, when we pull it down, is going to get pulled back up, right? And then once it hits the top, it'll come back down. And again, we've got oscillating motion. So what can we measure about this? And what can we calculate from those measurements? So all of those systems that we just observed are undergoing periodic motion, or another way to say that is oscillation, meaning that their motion is repeating itself over time. Now, if there were ideal instances of oscillation, then they wouldn't be losing any energy to non-conservative forces, meaning that the time that it takes to complete one oscillation will be constant and their motion will continue in perpetuity. Now, all of these systems we observed obviously are in the real world, so they are subject to non-conservative forces. And so there will be small but negligible differences between each oscillation, the amount of time it takes to complete each cycle, and eventually over time they are going to lose energy and they'll come to a stop. Oscillations, what we call oscillations, are the regular variations in magnitude or position around a central point. So again, every system we just observed is oscillating, and one oscillation is the cycle it goes through as it repeats itself. So we can think of another example, something like a ruler, and if you pull a ruler back from its equilibrium position, then we can bring it back to this position like this. And once we release it, it's going to cycle back and forth, bounce back and forth between its extreme position over here and then its other position over here, going through the equilibrium position and bouncing back and forth. And that's what we call an oscillation. We go from one end back to the other would be one oscillation. So we can think of some examples of oscillating systems, and given the definition that we just gave and the examples that we already took a look at for the systems that we observed, can you come up with some examples of, in the real world, what sorts of examples we have for oscillating systems? So please take a moment to pause, and if you want to write them down, might not be a bad idea, and then we'll come back and we will come through and go through some examples together. All right, so we observed a pendulum as one of our systems. We can think of ocean waves. Ocean waves will go through oscillations. They will go up and down, obviously making a wave-like pattern or a sinusoidal pattern, which will be very important to oscillating systems. String instruments will make something very similar. They will make and we'll take a look at this in just one second, but they will make a pattern just like this when you pluck a string instrument. So they are examples of oscillating systems going back and forth as they vibrate. Springs, as we saw in the systems we observed, will go back and forth in oscillating patterns. Earthquakes essentially are ocean waves, but through the ground. And so they obviously are also examples of oscillating systems. And finally, we've got light. So photons of light are electromagnetic waves. And again, they follow this wave pattern. And so they are oscillating, vibrating as they move through space. And really, all particles will do that same thing, just like photons. And so, since all particles make up matter and they're also moving through these oscillating motions, that's why studying oscillating systems is very important to our understanding of the world around us. All right, so we're going to take a quick look at this video, and we will watch this again and discuss in class. But just take a watch and think about how the strings, observe how the strings act when they are plucked. All right, so those strings were undergoing oscillations, right? And any oscillating system, we can describe the periodic motion of such a system in a few different ways. So let's talk about how we would do that. So first of all, every system is going to have an equilibrium position. For those strings, it was when those strings are straight before they are plucked, right? For the system over to the right here, we have a position where our block on the spring would be, and it will sit when there are no forces acting on it, right? So this is our XEQ. And this is the state that it will be in, the position it will be in when its net force is zero, right? So if its forces are zero, the forces net out to be zero on it, then it will be at a state of equilibrium. Now we can take and we can displace that system elsewhere, right? So this system right here, if we took and we pulled it over to the right, it's going to have some distance that it moves, some displacement away from that equilibrium position. There are some special points along the positions where it will move, the most important of which is its amplitude. So the furthest that it moves away from its point of equilibrium, we call that position its amplitude, which we can represent with the letter A. And that's the maximum distance that it gets away from its position of equilibrium. Now, that it will move that distance in one direction, but it will also move that same distance in the other direction as it oscillates back and forth, right? So this position over here, if we define this as the negative direction, is negative A. So A is worth of distance away from its point of equilibrium, but in that negative direction. And we think of one complete cycle as it going through this whole motion once. So if we started at A, then it would move towards its equilibrium position and then keep going through the equilibrium position until it gets to that negative A position, then start moving back towards that equilibrium position and move through it until it gets back to that position of A again, all right? And that is one cycle. We can start at any point in this cycle and then wind up back at that same point as long as we've gone through all this whole motion one time. So for instance, what we can't do is start from A and go to negative A. If we just do that, going from here over to here, that would just be one half of a cycle. The same thing if we went and we started from our equilibrium position and then moved through negative A or A back to our equilibrium position, that's only one half of a cycle. So one cycle is completed when we move all the way through this entire cycle one full time. All right, so let's take a look at displacement using actual oscillating system here. So we have our weight on the end of a spring again, and it's important to note that right here is its equilibrium position, right? Now, its equilibrium position is the position where the net force acting on the system is zero, right? If we drew a free body diagram for this system, or for the weight at the end of our system, right? We have the force of gravity of the weight pulling down, and then we have the force of the spring pulling back up, right? It's not the force of spring is exerting 0 newtons worth of force, and it's not the force of gravity is exerting 0 newtons worth of force, but the net force here at equilibrium, net force equals 0 newtons, right? These two are equal to one another. And so at this point, that's why we don't have any motion, right? No acceleration in one direction or another. And so we can take, and let's get a little marker for where this weight hangs. This is about 34 centimeters, all right? And then let's pull this out of equilibrium, all right? So however far we pull it, when I apply an external force applied right here, away from where it would naturally sit with 0 net force as point of equilibrium, I'm gonna pull it down to 24 centimeters. 24 cm, all right? And then we'll release it. And obviously when we release it, we'll see some oscillating motion. And if I'm good, I can catch it. And since we measured each of the other points at the bottom of the weight, we can measure its topmost position up here is at about 44 centimeters. And then we can drop it back into its oscillating motion. And it continues to oscillate between 24 centimeters and 44 centimeters, right? So what we've got is, again, its point of equilibrium is right here. This is our X EQ, our point of equilibrium. And if we define that as 0, as our 0, right, then we're going 10 centimeters down in that downward direction. And if I call that positive 10 centimeters, then the weight is also jumping back up and it ends up at the top of its oscillation at a position of negative 10 centimeters, right? So we've got the maximum displacement is our amplitude, right? And we also have our amplitude in the opposite direction, or negative A. And we have our point of equilibrium, which is where the system would rest if we didn't pull it out of equilibrium, which is where it wants to rest, all right? So again, we can put this back in and start oscillating once more. Isn't that fun? All right, and since a cycle is the completion of a single round trip in an oscillating system, we can describe that in a few different ways. The first way we could describe it is with the period that it takes, which is the amount of time that it takes to complete one cycle. And we would typically measure this in seconds, right? So if we started in the system described by the diagrams, on this furthest displacement, we would have to move through the equilibrium position, back to the furthest displacement in the other direction, back through the equilibrium position, and then finally back to that original position. And the amount of time it takes to do that would be the period for this system. Another way to describe this would be using frequency, and frequency is the number of cycles or oscillations that this system does per unit time. And we often measure the cycles of seconds. We often measure this in cycles per second, or in burst seconds. That's -1. Or we have we've designated a specific unit for that, which is hertz. And I'll show you what that means in 1 second. And it's important to note that our frequency equals 1 over our period. And 1 hertz equals 1 cycle per second, or 1 hertz equals 1 over seconds, since cycle isn't really a unit. We can also describe this as inverse seconds, s to the -1st. equals 1 over seconds equals 1 hertz. All right, so let's play around with that equation and put some numbers to it. So for an example, we've got a medical imaging device that produces an ultrasound by oscillating with a period of 0.400 microseconds. So we've got a period, t equals 0.400 microseconds. And 1 microsecond is 10 to the negative 6 seconds. So that's really 0.400 times 10 to the negative 6 seconds. Or if we wanted to put that into scientific notation, that's 4.00 times 10 to the negative 7th seconds, right? And we want to figure out what our frequency is. So we know that frequency equals 1 over t. So frequency is the inverse of our period. And so if we take 1 divided by our period, 4.00 times 10 to the negative 7th seconds. 1 divided by 4 is 0.25. And then 1 divided by 10 to the negative 7th is 10 to the 7th. So that really gives us 0.25 times 10 to the 7th inverse seconds. And if we wanted to clean that up a little bit, we could put that into scientific notation, which would be 2.50 times 10 to the 6th inverse seconds. Or we could also call that hertz. So that's the frequency of an ultrasound that's oscillating with a period of 0.400 microseconds. All right, here's our second problem. The frequency of middle C on a typical musical instrument is 264 hertz. What is the time or the period for one complete oscillation? So we've got our frequency equals 264 hertz, which means we got 264 cycles per second, for every 1 second. Right? So if frequency is the inverse of period, then to get period, let's bring period into the numerator by multiplying by period, and then we'll divide by frequency. And so we end up with period equals 1 over frequency, or period is the inverse of frequency, which since frequency is the inverse of period, that makes sense. So if we want to find our period here, we'll take 1 divided by our frequency, which is 264 inverse seconds. So 1 divided by 264 will give us 0.00379. And since inverse seconds was in the denominator, I'll bring seconds up to the top, or we call that 3.79 milliseconds. Will be the period, the amount of time it takes for the string on a typical instrument to vibrate 1 time at the frequency of middle C. So as a system oscillates, what is causing it to move through those cycles is what we call a restoring force. A restoring force is the force that causes the system to return back to its equilibrium position. Remember that equilibrium position, if we think about this ruler getting flicked between 2 positions while being held. The equilibrium position is right at the center where it would just be sticking up if no flicking had happened, right? However, as the equilibrium position is reached, the kinetic energy or momentum of the system that it possesses will carry it past that position back into disequilibrium. So if we look down here on the bottom images, we've got as we flick the ruler and pull it back into this position, we've got a force pushing it to the right, back towards its state of equilibrium, right? But as it moves to that position of equilibrium, then it now has some velocity or some momentum in that direction, right? And so once it gets to that position of equilibrium, even though its net force is 0 here, its momentum is going to carry it through here until it gets to the other end. And once it hits that other side, then it's going to have some force pushing it back towards equilibrium again, right? And eventually it hits the end where it reaches its position of amplitude, its maximum displacement, where it's going to have 0 velocity. But by now, it's got that force pushing it back. So that's going to cause an acceleration that is in the same direction as the force, right? And as it accelerates, again, it'll pick up velocity. It'll be moving through its equilibrium with some velocity and some momentum that will again return it back to that original position of disequilibrium that we flicked it into in the first place. And so this is why it continues to oscillate back and forth, because that restoring force continues to push it back towards equilibrium. But once it hits that equilibrium position where it has no force, then it already has momentum that'll push it back into a state of disequilibrium. Yep. So this restoring force continues to accelerate it back and forth through its equilibrium position, and the cycle will repeat until the energy is dissipated to non-conservative forces, and the object/system has returned to the point of equilibrium without momentum. So eventually, it'll get back to this point of equilibrium once all of the energy has been dissipated to non-conservative forces like air resistance or friction or anything like that. All right, now let's take a look at that restoring force using the example of our mass on the end of a spring again. All right, so again, I'm going to judge our position based on the bottom of this weight. And so right now we're at the equilibrium position, right, which we're calling 0 meters. And if we drew a free body diagram for this position right here, there are two forces acting on the mass, right, is the force of gravity pulling it down and the force of the spring pulling back up. And in this position, those two forces are equal to each other, right? So we have a net force of 0 newtons. And that's why this is our equilibrium position, right? Unless we acted on this with a net external force, nothing's going to happen with the weight at this position. However, if we bring it out of equilibrium, let's say to our position where x equals our amplitude, x equals a, so right down here, now we've stretched that spring, right? So our force of gravity is going to be the same as before. Right, our force of gravity will still be equal to up here. The mass hasn't gained any additional mass, so the Earth will not act on it any differently. It still has the same force of gravity. However, the force of the spring has increased once we get to this point right here, right? So once we get there, now our force of the spring is significantly larger. This is our restoring force, right? This is going to be pushing us in that upward direction, accelerating us if I let go of this weight, then that force is going to accelerate it upwards, right? And I can bring this to any point along here, right? Remember Hooke's law, as I stretch the spring more and more, the further I stretch it, the more that force increases. So the force right here is not going to be as large as it is up here, right? Our net force is going to be at its maximal point, either at the bottom or the top of the oscillation, right? So at any point along here, we'll have force. Any point below XEQ, our equilibrium point, we will have a net force pointing upwards, right? It'll be strongest down the bottom where our velocity will be 0. And then if we allow it to bounce, we'll get that oscillation again, right? So let's think about up at the top. At the top, we're going to have our restoring force, our net force is going to be pointed downwards, right? Because as we get up, as we decrease the displacement, the stretch of this spring, we're going to get to eventually a very small spring force, right? And so up here, our force of gravity is still the same as it ever was, but now our spring force is very, very small. And since our spring force is very small, it's outweighed by our force of gravity. So our net force is now pointed downwards. And again, up at the top, that's going to be our maximum amount of net force we're going to see in the downward direction. And if we look any point along here, we're going to have some additional force in the downward direction versus what's upward. So our net force will always be pointed downwards up in the top half above our equilibrium position, right? So any point along here, we'll find that we'll have a net force in either direction. Where we won't have a net force is where we're at our equilibrium position, right? We'll have a net force. Our force of the spring equals our force of gravity. However, at that point, we already have some momentum, some kinetic energy bringing us upward or downward, depending on which direction we're going. And so we're going to move through that equilibrium position and then start accruing forces in the opposite direction, pushing back into that equilibrium position. And that's why this is called a restoring force, because it will restore us back to equilibrium. That's the direction that the net force is pointed once we're displaced away from that equilibrium. The systems that we've looked at so far are what we would call simple harmonic oscillators. So an oscillating system can take many different forms and follow different patterns. The simplest of which is what we call a simple harmonic oscillator. And a simple harmonic oscillator, or an SHO, is an oscillating system that is caused by a force that abides by the following rules. The first is that it has a restoring force. The force is always pointed towards equilibrium. And secondly, that force is proportional to x. So it's proportional to the displacement of the system away from that equilibrium position. And if this sounds familiar, it means that a simple harmonic oscillator has to follow some approximation or analogy to Hooke's law. And just as a quick reminder, Hooke's law, we see up on the top right of the screen, says that the force of a spring is equal to the opposite of the spring constant times the displacement of that spring, meaning the force of the spring is equal to some constant times the displacement, and then it's in the opposite direction as that displacement. And if we have a perfect simple harmonic oscillator, then we're going to fluctuate. And again, perfect just meaning that we're not losing anything to non-conservative forces. And if a simple harmonic oscillator is perfect, then it's going to fluctuate between A, so our maximum amplitude, and negative A, our maximum amplitude in the opposite direction. And it's going to have an overall range of 2A. And it'll just continue doing that forever and ever, so long as there aren't any forces that are dissipating that energy. However, non-conservative forces, which obviously exist in the real world, things like air resistance or friction, they're going to cause what we call damping or dissipation of the energy contained in that simple harmonic oscillator, which means that its oscillation will be damped over time. And so eventually, rather than continuing to oscillate forever at the same amplitude, that amplitude will decrease and decrease and decrease until the system eventually comes to rest once all of that energy has been dissipated to non-conservative forces. So just as a quick review of Hooke's law and energy contained in a spring, Hooke's law is that the force of a spring equals negative k, the spring constant, times delta x, the displacement of that spring. And if we want to think about the potential energy stored within a spring object system, we would calculate it like this. Our change in potential energy stored in that spring system is equal to 1/2 times k, the spring constant, times the displacement squared. And just as a quick reminder, k equals spring constant, which is a proportion of the displacement of the restoring force, and is measured in newtons per meter. And x is our displacement, or the deformation of our spring, and that's measured in typically in meters. All right, so in class, what we'll do is each of those three demo systems we looked at the beginning of this video, the carts on two springs, the mast on the end of a spring, and the pendulum. You guys are going to take those and try to determine and quantify all these different variables related with simple harmonic oscillation for the system that you're looking at. All right, so that's what we'll do in class today. Thank you so much for learning this lesson.